Welcome everybody. The second English talk of the day. The next speaker is a friend of mine. He comes from Udine. You are recently graduated in computer science from the University of Udine, and he is here to tell us why TLS sucks. He started Fenrir Project more than 1 year ago, right?
Yeah, a couple of years ago.
And so it's a beautiful, huge code base, well documented. So, ladies and gentlemen, Luca Fulker.
So hello everybody. This is, as you can see, about a completely new protocol that aims at replacing both TLS and other layers such as lower layers like TCP, UDP, and upper layers like I don't know, OAuth for authentication and other stuff. It's a formally verified protocol in the sense that I started as with a mathematical model and tried to verify that all the interactions of the model were safe. The verification has been done in ProVerif. You can always find everything on the website, along with all the thesis if you want all the details, and a tentative paper still in draft. Anyway, it's still a work in progress. Parts of it are done. It's not really at a usable state yet. What this is about? This is about design choices and the ramifications in the whole protocol pile. Again, since we are trying to make something new that replaces both TCP throughout, we need a new packet format. We'll see a little different trust model, and the whole objective of this project is decoupling applications from their security. All of this is inside a federated environment, so basically we try to do what OAuth has done wrong, and at a lower level. The first question is, do we actually need a new protocol? There's a lot of old transport protocols. Some of them, like the newer Quick and Minimality, include actually encryption. And then we have authentication and some light form of authorizations in the upper layers like Kerberos, OAuth, and SPID. For those of you that do not know what SPID is, it's a rather new protocol made by an Italian politician, which should already scare you. You can find the specification in Italian only on the web. If you like to break stuff, have a look at it. You'll probably find a lot of stuff. I actually helped trim away a lot of unneeded and almost broken stuff, but it's the process that protocol went through was not really formal, so go play with it. Again, there are a lot of protocols, and when you design an application, the first thing you do is try to decide what your stack will be. So the usual thing you see is something like TLS on top of TCP. Again, you will probably use OAuth, so all the HTTP cookies and etc. If you actually try to see and the various features that each protocol implement, you will find a lot of duplicated stuff, like the session protocol. TCP has a session, TLS has a sessions, HTTP does not support sessions, so you have to reintroduce it at the cookie level, or OAuth has its sessions, and the application has to put it all together. Layering was introduced in the OSI model to abstract things, and the idea was to have completely independent layers so that the final application layer would be simple. It turns out that in this and a lot of other cases there are both duplicated features and the complexity is pushed up to the application level. It gets worse when you want to do some more advanced stuff, like I don't know, a reliable connection for your control data, an unreliable connection for, I don't know, audio or stuff, or maybe even multicast. All your application will end up having to keep all this together by itself. This is not what the layering was originally about, and yeah, it was about taking complexity away from the application. We ended up pushing it towards the application. Quick and minimality try to take away and simplify a couple of things there. So, for example, quick and minimality put together the TCP and TLS layer. They do it in slightly different ways. They both are just only reliable connection protocols. You can hack quick to be an unreliable protocol too, but it's more of a hack again. And again, if you want authentication, you will have to use upper layer protocols, which, as we will see now, will try to introduce some federated environment. In the case of OAuth, is a broken federated model, and they try to put it all together in the browsers, which ends up being your biggest point of failure. Fenrir tries to work at both the lowest level, so for any kind of data transport that you might need, and the, let's say, TLS level for all your authentication encryption needs, and the authentication again and the authorization for what OAuth is supposed to do. If you look at the speed workflow, which is a lot similar to the OAuth workflow, you will see your application trying to contact the service, your web server, whatever, which gets redirected through your browser to the identity provider, which is just an authentication server. You log in, then you get redirected again to your service. This was done because it was an initial test, an initial way of decoupling the application from the management of the security that goes all through the browser. So this is all redirects, and the login is actually going to be handled through the browser. But OAuth and speed do not enforce this, so you can actually do a lot of these redirects inside your applications. There have been applications that use your browser, but then put a transparent window on top of it just to get your password again, so they can log in again without confirmation again. And really, you just made your browser another password manager, and it's a password manager with a huge attack surface. It doesn't really sound that right. Again, as we've seen before, we have 4 different roles: an application, a client manager, Secondo, which in the previous example was the browser, your authentication server, and the actual service. In Fenrir, all these different roles are strictly enforced and designed so that, for example, the application and services do not have any access to things like user databases, tokens, or other stuff directly connected to the authentication itself. It also simplifies the development because not only you do not have to do again authentication and system management, but as we manage a lot more data transport models, also the old multi-stack argument I I explained before is going to be a lot more simplified. If you're curious, the federation is completely token-based. There is the algorithm itself. It requires no clock synchronization at all, like, for example, Kerberos or even OAuth to Athu that requires a loose kind of clock synchronization. The service that you're going to connect to is identified by just its identifier. You do not have the common protocol port for the identification of your service. Again, since it's a federated environment, it means that everything is centered around the authentication server, which is starting to sound like another big point of failure. We will see that it is really not, as there are a lot of shared secrets behind the scenes, so that even if the authentication server is compromised, your data on the service will actually still be safe, and the authentication server will not be allowed to impersonate its users. A loose view of how the workflow is something like your authentication connects to its client manager to tell that you want to connect to, I don't know, google.com. This is all on both of these are on the same machine. The client manager authenticates to the authentication server, which connects to the service telling that a newer user has been has just connected. The service will generate the keys, which gets forwarded to the application that can finally connect to the service without any more handshake or other stuff. Again, there are shared secrets between the manager service and the authentication server, so the authentication server forwards these keys but cannot actually use them as such. Lower level, this is how the packet looks like. This is the older view of the TCP headers plus a TLS header, which is well, a bit verbose, and a lot of stuff is clear text and very few is encrypted. This is the basic stuff that you will find of on the Fenrir protocol. The connection is identified by connection ID, so no source port, destination port, IP address, just a connection ID. A little bit of an encryption header to decrypt each packet individually. All the green stuff is encrypted, and this is actually a stream-based protocol. So we can have multiple streams even in the same packet that have their identification, counter, and data length. Again, no big stuff, but each and every stream is completely independent from one another, and we can have all kinds of streams: reliable, unreliable, ordered, unordered, data stream, or datagram. So, for example, a TCP connection would be a reliable ordered data stream, and UDP connection will be something like an unreliable unordered datagram stream. But there are also more interesting combinations like reliable ordered or unordered datagram delivery, so that you don't have to manage the beginning and the end of your messages. Also some pretty useless stuff like unreliable unordered data stream, unless you can figure out what each single byte means. But yeah, why not? Again, since each connection is identified just by a connection ID, we have simplified a lot of things like multi-homing, roaming stations. We don't care about what IP we are seeing. There is a requirement of one round trip to actually check that you are allowed to use that IP address, so you don't actually flood some third party. But yeah, it simplifies a lot of those things. Multicast is gonna be supported too, and also that's a little bit trickier, because we cannot actually use a standard HMAC where the keys are shared between everybody, as everybody will be able to forge the packets. So you will need fast public key cryptography for that. Probably only HHC support that. Some good stuff on the reliability side. I created this new library that implements the Raptor Q algorithm that basically generalizes the old RAID 5 concept for disks. Basically, imagine you want to send 10 packets with 30% of chance of being dropped during the transmission. You send your initial 10 packets plus 3 recovery packets, and once the receiver gets 10 packets of any combination repairs those packets, you can actually get back the original 10 packets. The project is freely available, works. Some new stuff was going to be added in about a month. There might be some software pattern problems, but I'm Italian, no software patterns here. Don't really care. This will enable both reliable connection without the use that you can use to you can combine together to get the original 10 packets. You're not actually granted that you will get them, but it's something like 1 chance in a million, and it gets 100 times lower for each additional recovery packet. This has actually been tested, and you have all the tests to actually follow the RFC that describes it. Yeah. 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 Give me time. I haven't had much yet. Okay. Then thanks again, and see you next talk.